Welcome back to the final part of ELEC142 Problem Sheet 3 solution. So this is going to answer question 3. This is the most difficult question on this problem sheet, but it's a very similar form to something we've already done an example of in the lecture, so hopefully it shouldn't be too much cause for concern for you. So just follow it through step by step, and if you've been able to solve question 1 and 2, this shouldn't be too much of a problem for you. Just be careful with your working and don't jump too many steps in case you miss something out and make an error. So if this sort of question was asked in an exam question, please remember to show your working, and if you do make a small mistake somewhere earlier on in the calculation, if I can follow and understand your working, you'll still get most of the credit for the work you've done, providing obviously you don't make more mistakes as you go along. If I can follow your working and your process is sound, a small mathematical error carried through will not cost you too many marks. So in this question we're asked for the circuit shown in figure 3, redraw the circuit with one single impedance element, calculate a value for this and find an expression for the current I of t. So once again this question is helping us through, telling us what we need to do to solve it. So what we need to do is we need to replace all of these components with a single impedance, which we're going to call Z total. So this is very similar, this step of the question is very similar to what we've gone through in the lecture. So here's a lecture slide that we went through. So what you've got in this example is an inductor in parallel with a resistor and a capacitor which are in series, and we went through the process to show how we could convert it to a single impedance. So what you need to do is first of all convert the elements in series into one resistance, which we did here, and then we need to convert these impedances which are in parallel into a single component, which we did here. So there's two different steps to the calculation. You need to deal with the components in series first, then deal with the parallel part. So that's what we've done here. So question 3. There we go. So what we're aiming for is to go from this configuration to this configuration where we just have one impedance element which we draw as a resistor, and we've given it the name of Z total. So what we've got here is our voltage source. This is a little bit different. This is presented as having a magnitude of 12 root 2. When we go on to talk about RMS values in later lectures, you'll understand why this RMS term and the root 2 is significant. So all we've done is we've just converted this, our voltage, into our phasor form, as we always do when we solve these questions. So the magnitude of this is 12 times root 2 at an angle of 0 degrees, and that gives a magnitude of 16.97. Then we're going to write an expression for our current I of t, and we know this is a peak current, a cosine of 5000 t, which was the same as our voltage source, that's our value of omega, plus a phase shift phi, which we don't know what it is yet, and it's going to be in amps. So now we've done that basic work, let's go on and find the impedances of our components. So we've got three different components. We've got a resistor, an inductor, and a capacitor. So let's find the reactance, or to give it the proper name, the complex impedance of each component. So for our resistor, Z of R is equal to R, which is equal to 20 at an angle of 0 degrees in ohms. That's the polar form. We just know that it's 20 ohms and there's no phase shift because it's a resistor. And we can write this in rectangular form as 20 plus 0j ohms because it's all along the real axis. There's no imaginary component to this. For our inductor, ZL is equal to j omega L. So this is equal to omega we had up here, that's 5000. So just put that value in there, times the value of our inductance, and that's 3 millihenries. So that value is in there. And that becomes J 15 ohms in rectangular form, which we can also present in polar form. Just put that number into your calculator and we see that we have, well, a calculator, or you can just visualize it because it's just an inductor, it's quite simple. So we know in polar form this has a magnitude of 15 at an angle of 90 degrees. And that's also in ohms. And then ZC for our capacitor is equal to minus J 1 over omega C. So all we're doing is just going to put our values in. So our omega value is the same as before, it's 5,000. Put in the value of our capacitor, which was 10 microfarads, so that's 10 times 10 to the minus 6. If you work that out, you'll get a rectangular value of minus J20, which if we convert into polar form is a magnitude of 20 at an angle of minus 90 degrees. Remember, it's a capacitor, so it's going to lag. The voltage across the capacitor lags the current by 90 degrees, and that's basically what we've got here with the complex impedance. That's that effect you can see. So it's the opposite phase shift we had from the inductor. So that's the first bit done. You'll notice that I've got each of these written in the polar and the rectangular form. The reason I did it at this stage is because we're going to want to use sometimes the rectangular and sometimes the polar form. So if I've written it here, it's easy for me to refer back and see which value I need to use instead of having to do a conversion each time. So let's start to simplify our circuit. First of all, we're going to deal with the components that are in series. So we're going to find the total impedance for this section, this branch of the circuit, and that's the resistance in parallel with that in series, the resistance in series with that inductor. So we're going to call that ZRL, and that's equal to ZR plus ZL. So let's work that out. What we've done is I've put I've phrased the question in rectangular form. The reason I've done that is because it's an addition, it's easier to deal with in our rectangular form. So for the resistor, it's 20 plus 0J, plus for the inductor, which is 0 plus 15J. So if you just add that together, it's 20 plus 0 plus 0 plus 15, which gives us 20 plus 15J. So that's our answer there. I've also then converted it to polar form here. These two numbers are the same, they're just in different forms. And again, I've written them both down because when we need to use them, we can either use the rectangular or the polar, depending on which makes our calculation easier. So now we've done that, we've got our circuit which is looking like this. That was our first step to solving it. So now this looks a lot simpler. We have this value for the impedance here, and we can see that's in parallel with our capacitor. So we can now calculate the next step. To go to here, this kind of version, we want to find Z total, and that's going to be the impedance of that capacitor in parallel with that complex impedance of the series combination of the resistor and the inductor, which we know. And using this equation, it's the same as for resistors in parallel. If there's only two, we can use this simplified form where it's the product over the sum. And because we've got a product and a sum, that's why it's useful to know what both the polar form for the multiplication and the rectangular form for the addition are. So I've just put the values in. So ZC is a magnitude of 20 at an angle of minus 90 degrees, and we need to multiply that by ZRL. So I've just pulled that value down and put it in there. For the sum, it's easier to work in the rectangular form, so I've just put those values straight in there. Then we can perform this calculation. So on the top we get 500 at an angle of minus 53.13 degrees, and then for the bottom we get 20 minus 5J. Next up, we want to convert 20 minus 5J into polar form so we can do the division, and that's what I've done here. Just put it in my calculator and get that value. Then finally, we can actually perform this calculation. So 500 divided by 20.6 will give us 24.3 or thereabouts at an angle of minus 53.13 minus 14, which gives us minus 39.13 degrees, and that value is in ohms. So we've finally got our value of Z total is 24.3 at an angle of minus 39.13 degrees ohms. So that's our total value there. So we've solved that first part of the question. So we've calculated a value for that single impedance element. That's mostly done. Now we've done the hard work, we're just going to find the expression for the current I of t. So this is quite simple. Now we've got this easy circuit configuration. We know what the voltage is, we know what the impedance is, so we can find the current using I is equal to V over Z. That's just the same as using I is equal to V over R in a DC circuit with just resistors. So we're going to put our values in. V is our phasor form, which we had at the beginning of the question, and then we're just putting our Z total value in here as well. So perform this calculation, we get I is equal to 0.70, so that's 16.97 divided by 24.3 at an angle of 0 minus 39.13. Sorry, 0 minus 39.13, which gives us a positive value. So that's our value for our current. I is equal to 0.70 at an angle of positive 39.13 amps. So our final step, we're just going to convert that into our time domain form because we were asked for I of t. So this is what I was saying about once you've solved it, yes, we found an expression for the current, but let's read the question and make sure we've answered all that was asked of us. We've been asked for the current in the form of I of t, so make sure you do that final step and get the credit for it because you've done all the hard work. This step is dead easy. So you just move the magnitude down. You've got omega from before. We know it's a cosine because that was what we started with. And then you need to add this phase shift term. So that's the final answer for the current. So just to show, this is what we've simplified our circuit to. So we started with this form of the circuit. And what we've ended up with by manipulating our circuit is this. It's a lot simpler. We've got our voltage sources we had before, and we've replaced all of those circuit elements with a single impedance element here. And then using that, we managed to find our current. So that's our circuit characterized. Hopefully you managed to do that. Good work if you did. Give yourself a pat on the back.